Good morning, everybody. Welcome to Argonne National Laboratory's Science at Work webinar series. Today, we're going to hear about clearing the path to recycling batteries at scale. My name is John Harvey, and I'm a business development executive in our Science and Technology Partnership and Outreach organization. Before we get started, I wanted to provide some logistical things. We found that it works best if you have your VPN off. If you're having any technical issues, we recommend logging off and logging back on to get started. And we encourage folks to ask questions in the public chat window. Because this is such a short event, we will not have a chance to answer those questions during the session, but will respond after the session is ended. Finally, also note that the webinar is being recorded and the recording will be made available at the end of the session as well. Now I'd like to introduce our speakers for today, Jessica Durham and Albert Lipson. Jessica is a materials scientist at Argonne and is part of Materials Recycling R&D Group, working in the Materials Engineering Research Facility, or MRF, as we call it. She's also a lead investigator in the Department of Energy's Resale Center for Advanced Battery Recycling. Albert Lipson is a principal materials scientist at Argonne and is part of the Materials Recycling R&D Group in the MRF. He leads projects to advance state-of-the-art in recycling lithium-ion batteries and developing lithium-ion battery cathodes. We'll start with Jessica. Jessica, we look forward to your remarks.
Thank you for the introduction, John. Good morning, everyone, and thank you again for attending our webinar. I'd like to start today by talking to you about recycling lithium-ion batteries. As the demand for electric vehicles grows, recycling of lithium-ion batteries will be critical when these vehicles reach their end of life. Recycling is not only important for keeping lithium-ion batteries out of the landfill, but also to allow the U.S. to capture critical materials inside of these batteries and reduce reliance on foreign countries. The Department of Energy's first advanced battery recycling R&D effort, the Resale Center, is working to help grow a globally competitive U.S. recycling industry. The Resale Center is a partnership between Argonne National Lab, Oak Ridge National Lab, the National Renewable Energy Laboratory, UC San Diego, Worcester Polytechnic Institute, and Michigan Technological University. The problem with lithium-ion battery recycling today is that batteries from electric vehicles and stationary storage applications typically cost money to recycle. That's because the recycling methods around today use high amounts of energy, require extensive processing, and generate waste. These methods include pyrometallurgy and hydrometallurgy. Pyrometallurgical recycling involves heating a battery at high temperatures to burn off the carbon and recover metallic components. On the other hand, hydrometallurgical recycling consists of dissolving metal-based battery components in acid and generating metal salts that can be put back into the battery cathode manufacturing process. Profitable recycling is needed to drive a healthy electrification infrastructure. Therefore, other options for recycling are being considered. This is where DOE's Resale Center comes into play. Argonne National Lab leads the Resale Center, which focuses on a third way to recycle lithium-ion batteries, and this is called direct recycling. Direct recycling involves maintaining the original chemical structure and process value of battery components by recovering, regenerating, and reusing them directly. By retaining the value of the original battery components, a lower cost upcycled material can be supplied to battery manufacturers. However, there are several challenges associated with direct recycling. One of the first areas of concern is contamination, which can happen while breaking down batteries. Using crushing, milling, or shredding processes, which are standard, creates fine particles such as aluminum or copper nanoparticles, which are difficult to separate from powders and can affect performance if it ends up in the recycled material. Another challenge associated with direct recycling is separating cathode materials that have both similar compositions and processes. Think of this as separating different types of NMC materials from one another. This is very challenging. Finally, one of the biggest hurdles to cross is figuring out how to upcycle materials. Cathode materials that we're currently getting back from batteries were made 10 years ago and aren't typically relevant to the battery industry today. The important question here is, how do we upcycle cathodes? For example, going from NMC 111 to NMC 811 involves stuffing a lot more nickel into the structure. So how do you do this without destroying the structure and also while maintaining good performance? Now that we have gone over how to recycle batteries and some of the associated challenges, I will hand the presentation over to my colleague Albert, who will introduce the scalable processes being developed in Resale to directly recycle lithium-ion batteries and produce clean streams of valuable materials.
Thank you, Jessica. So yeah, I would like to talk to you today about how we're actually trying to bring these processes to reality in the Resale Center. And so what we've done is really tried to optimize the process, particularly for direct recycling. This is something that hasn't really been done that much before. So one of the things we needed to do at the start of this was to look at how do we actually disassemble the batteries and how do we do this shredding or hammer milling process. And so what we figured out was we tested a whole range of different shredders, and we've determined basically which shredder produces the least amount of fines and therefore the least amount of contamination. And that's what we're using to move forward with this recycling process. So once the batteries are shredded, the next step you need to do is to be able to remove the electrolyte material. This electrolyte contains flammable carbonates as well as the electrolyte salt, which is typically lithium hexafluorophosphate or LiPF6. So we get this off currently by simply rinsing in a carbonate solvent. We're then able to take the rinse out from that and then concentrate the rinse. And you can actually regenerate a working electrolyte from that concentrated electrolyte. After the shreds are rinsed, the next step we need to do is go ahead and remove the plastic separator. We're currently doing this by a very simple process that uses airflow that passes over the material as it's falling through a tube. This drags out the separator, and then we're able to collect it separately from the rest of the stream. And then at this point, you basically have shredded material with electrodes intact. And we need to be able to get the electrode materials off of the foils. And we have a number of different methods to do this. There have been some solvent-based methods developed elsewhere in the Resale Center. And here at Argonne, we're working on thermal-based methods to be able to remove the binder as well as the carbon black that's used to make these electrodes. Once you have the bare powders, you now have a mixture of cathode and anode powder together. We need to figure out a way of separating these. And so Michigan Tech actually came up with this idea to use a mineral processing approach called froth flotation to actually separate these materials out. In this process, what you essentially want to do is you add different types of collector materials that change the surface chemistry of the particles. You want to make one hydrophobic and the other one hydrophilic. The hydrophobic particles will then attach to bubbles that you introduce into a column, and then they'll float to the top of the column. And then the hydrophilic materials will then sink to the bottom, and then you can collect the two fractions. So we've shown that this works really quite well for anode cathode separation, getting the graphite and the lithium nickel manganese cobalt oxide or NMC cathode out. We've also actually figured out that you can separate different cathode materials from each other. So particularly, we've shown that lithium manganese oxide and these NMC cathodes can be separated from each other. So at this point, we have separated cathode and anode. Now we need to recover the cathode material. So one of the last steps we need to do is actually add lithium back into that cathode material, because during the cycling process, the cathode will lose lithium into the SEI that forms on the graphite material. The SEI is the solid electrolyte interphase. And from that, we're actually able to regenerate the cathode. So we do this by just heating it with some lithium hydroxide, and we get back a cathode material that actually performs quite well in cells. So from these different processes, we've actually formulated an entire process that actually works together. And recently, we've demonstrated going from a shredded battery to cells that are actually working here at the Resale Center. And with that, I'd like to send it back to John to lead the Q&A section.
Great, thank you, Jessica and Albert, both for the compelling talk. Looks like we do have time for a couple questions. So let's get started with that. The first question is for Jessica. Jessica, what would you say are the challenges to get industry to accept recycled material?
Thank you, John. That's a good question. I would say two of the biggest things are purity and performance of the recycled material. For instance, industry typically has strict purity standards of 99.9%. In some cases, you can even add a few more nines to the end of this. And performance-wise, we've talked to industry, and they prefer to stay within a few milliamp hours per gram of the delivered capacity over time. And this is really important if you're using 100% recycled material in a battery. However, if we start considering only using about 5% of recycled cathode, we need to think about how that will affect performance. So if you just have 5%, a small decrease in performance might be negligible when you combine it with pristine powders. Therefore, the question I'd like to pose to industry is, can there be any compromise here? We'd like to hear more about industry's opinions on this, so please feel free to reach out to us after the webinar. Thanks, John.
Great, thank you so much, Jessica. And second question I'll throw this one to you, Albert. What are the next steps to bring the recycling process from the lab to reality?
So thanks, John, for the question. Yeah, so currently what we're doing is, now that we've demonstrated this process and we've seen that it actually works, we need to actually start to scale up these processes. So right now, a lot of the processes are running at lab scale, maybe 50 or 100 gram kind of scale. So we really need to get this up into the many kilogram scales and make all the processes continuous and look a lot more like what they would be in industry, so that we can get industry partners more interested in what we're doing. And during that scale-up process, we're going to need to find and identify the correct kinds of equipment that might be used in industry. And we're very interested in hearing from anybody in the audience who is either an equipment manufacturer or knows some equipment that might be useful to us in doing this process. And then the next step, once we've gotten these processes to a point where they're very close to what industry might do, we're really looking for industry partners to actually come join us. We would help you basically take our technology and set up an actual recycling line. And then from there, we'd really like to see batteries actually being recycled using the processes we've developed in the Resale Center. Thanks.
Great, thanks. Looks like we have one more that came in as well. So I'll throw this out and you guys can fight over who gets to answer it. But how do the environmental impacts of this method compare to those of recycling the metals as raw materials, for example, with hydromet processes?
So I can take that one if you want. So we actually do have some initial modeling of these processes in our model that is known as Everbat, that was developed here at Argonne. So in that model, we actually see that direct recycling dramatically reduces the impact of the recycling process from the perspective of energy, as well as carbon dioxide emissions from the process. This is because we don't have to go through a lot of the extra steps that they do to go back to the raw materials and then remanufacture the cathode material. And so we eliminate a lot of that. And we also potentially can eliminate a lot of the waste. Granted, we don't have a real working process yet. We don't have all the equipment. So these are just preliminary results at this point, but it does look promising that direct recycling could outperform the other methods from an environmental standpoint.
Great. Well, that's great to hear, obviously. So wonderful. Thank you again, Jessica and Albert. Really appreciate the talk. And thank you, everyone, for attending the event today. Again, I want to remind everybody that we will send written answers to the questions that you have in the chat, which there were quite a few, so thanks for that. Along with the recording of the talk, we'll send that out to everybody. Also, if you have any other questions, can provide any insights to the questions that were posed today, or would like to learn more about how to work with the laboratory, please reach out to us at partners@anl.gov. You can see that here on this slide. Thank you again. That concludes our webinar for today, and have a wonderful day.